Not necessarily. Looking for good researchers that aren't necessarily in medical physics. Yeah. They teach you about that.
Okay, let's begin. Everybody's quiet. You ready? I don't have to say let's begin. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Colloquium Program. Before I introduce today's speaker, there are some students I'd like to recognize. As many of you know, or you may not know, the Nuclear Criticality Safety Division of the American Nuclear Society sponsors a student paper competition every 2 years at a national meeting of the American Nuclear Society. We've been participating in this student paper competition for at least a decade, and we've always done well. Our students do well because they're outstanding students, and this past summer, at the summer meeting of ANS is no exception. We had 2 students present presentations, and they both walked away with awards, and I want to recognize those. They get cash, by the way. The first place award was won by Ibrahim Atiyah. Now, Ibrahim is not here today because he's teaching a class for the math department. That's what he does this time every Monday, Wednesday, and Friday. And so I want to recognize him, and I'll give him his check next time I see him. And then one of our new graduate students, Ibrahim is a senior graduate student, and one of our new graduate students, Shane Parkey, won the 3rd place award, and he also gets a cash award. And so, Shane, if you'll come down here, let me present this check to you. Ibrahim, congratulations.
Thank you, sir.
Okay. Let's give him a round. Okay, and now for today's presentation. The speaker is Dr. Martin Grossbeck, who recently retired from the Oak Ridge National Laboratory. Martin received a BS in physics from RPI, an MS in physics from Cornell, and then he did a 4-year stint as instructor in the Naval Nuclear Power School. Then he went back and finished his PhD at the University of Illinois in metallurgical engineering. After graduating from the University of Illinois, he joined the Oak Ridge National Laboratory, where he's been for the past 27 years, specializing in materials research. Most importantly, though, right after his recent retirement, he and I have been talking about his joining our department as a research professor for several years. It turns out that materials research is something that we've never really done much of. We're really weak in that area, and Martin brings strength in that area, and so we're glad he's here. And the title of his presentation today is Radiation Phenomena in Materials for Fission and Fusion Reactors. Martin, welcome.
Thank you, Dr. Dodds. I recall going to many colloquia as a graduate student, and the colloquium speakers would talk to the faculty exclusively to make sure that everybody knew they were at the forefront of their field, and the faculty sat in the first 2 rows of the room, and I noticed not a lot has changed, but I'm going to try to talk to the students today. I'm going to talk about some things that have been known for several decades, and I'm going to touch on some things that we still don't understand. So let me make a kind of a survey talk on nuclear materials. Oops. Okay.
There you go.
Okay. Not off to a great start.
That's okay.
Yeah, that was.
The problem is that era is on the top
Arrows
of
on
that.
there. Okay.
There you go.
All right, now we're off and running.
Yeah.
Okay, I said I'd talk about fission and fusion reactors, and probably start with fusion. Fusion reactors contain a plasma of reacting charged particles that are contained by a magnetic field, but at some point we have to have a first structural wall, and that's outlined in red on in this diagram. But the neutrons, of course, are not charged, and they will escape and penetrate the first wall and the blanket. Well, I've written down the simplest and most energetically favorable fusion reaction, and that is the DT reaction. So deuterium and tritium react to form helium and a neutron, and has a Q value of 17.6 MeV. 14 MeV of this is carried by the neutron. So the neutrons are what we have to capture to get the useful heat out of the reactor. To do that, there has to be a blanket surrounding the first wall that's cooled to extract the heat. Well, here's the neutron spectrum of a few research reactors and a fusion spectrum. Hit the wrong button. And what we notice is that in the mid-range, where a lot of the damage takes place, the spectra are very similar. But in the fusion reactor, we do have a spike at the neutron birth energy at 14 MeV. So to summarize, the neutron spectra of the fission and fusion reactors are sufficiently similar that most damage mechanisms in the materials are the same, but this high energy peak produces threshold reactions. We'll come back and discuss that a little bit more, but radiation damage occurs by primarily two mechanisms: atomic displacements and transmutations. Atomic displacements are shown diagrammatically here, where we have a neutron impinging upon materials, has to interact with an atom in the crystal and ejects a highly energetic and charged atom, which then can eject further atoms. So we get a cascade effect until there's no longer sufficient energy to eject an atom from its lattice. And the neutron can go on and also cause other interactions. So we get a cascading effect, and we said that they eject atoms from the lattice, so they produce an atom that's not in a lattice site, called an interstitial, squeezed in between, and where that atom came from is a vacancy. And at the core of that cascade, this diagram is showing we have something rich in vacancies, and then the interstitials usually are farther away. Just to put things in perspective, in an LWR, the materials may see about one displacement per atom. So that in a lifetime, on the average, every single atom in that structure has been displaced at least once. What saves us in an LWR is usually that the materials that are in the very high flux region don't stay there very long. At the fuel cycle, you change them out. On the other hand, on a liquid metal fast breeder reactor, there are a lot of structures that remain longer and are in a very high flux region, so we get damage levels of 50 to 100 dPa. These numbers sound small, but it means every single atom on the average is knocked out of its lattice site 100 times during the life of the material. In fusion, we may have 100 to 200. Well, we don't have any fusion neutrons or fusion reactors yet, so these are design goals. One time it was 400 dPa. I think people have backed off a little bit. The transmutations, this is supposed to be an alpha. We have N-alpha reactions that result in helium, and N-p reactions introducing hydrogen. So some of the effects of radiation, the most important ones, are swelling, hardening and embrittlement, which go together, and a rather interesting phenomenon, radiation creep. And I'm going to illustrate each of these. Swelling is a phenomenon where the vacancies we talk about precipitate and form voids. So they behave just like another chemical species, and a supersaturation of vacancies can lead to stable configurations of them, and they can grow as voids. And here we have a a micrograph showing stainless steel, first irradiated to 10 dPa, and you can see among some other features we have some voids, and then irradiating it to 50 dPa, the material is starting to look like a sponge. So swelling is not a minor problem. And just to put it in perspective, this is a before and after. That's a rod that was irradiated in the fast flux test facility at Hanford, Washington. Shows the fluence here are 1.5 times 10 to the 23rd, and that corresponds to about 75 dPa. And that's a 30% volume swelling increase. Well, I've also heard people, especially in the fusion community, say that if you could hold swelling below 1% or to 1%, everything would be fine. But let me illustrate that, because I have two rods. One is 0.3% longer than the other, which would correspond to a 1% volume swelling. And if I match the ends of these rods, this is how much it bows. So if we have even 1% swelling, for example, in fuel rods, there could be serious problems. Fortunately, there's another mechanism, a radiation creep, that will sometimes help us by relieving swelling stresses. Well, I also said that irradiation-induced defects that we talk about harden and brittle metals, and I've illustrated that by some stress-strain curves, again from stainless steel. And you notice here that in the unirradiated case, we have about 30 to 40% elongation. After irradiation, it's only about a quarter of that, and it has doubled in strength. Well, that's nice that it doubled in strength, but the ductility is something that's going to hurt us. Well, we talked about transmutations, and particular N-alpha reactions in fusion reactors. And one way, you might say, that to get around this problem is just to be very clever about choice of materials. But what I'm illustrating here is that if we look at the N-alpha cross-section for common structural materials, we find above about 10 MeV, they all have significant N-alpha cross-sections. Now you might say, well, let's stay away from nickel, that's a particularly bad one. But here, iron, chromium, titanium, and I could fill up that graph with a lot of other materials. But worse than that, I think it's safe to say that all reactors have some sources of helium. One is the boron-10 reaction, and here, as you're probably familiar, boron-10 absorbs a thermal neutron and produces helium and lithium-7. And this can be important in LWRs, for example. We have stainless steel core components. Stainless steels typically have boron concentrations of 10 to 30 ppm. And 1 weight percent boron will ultimately burn to 1 atomic percent helium. So we'll talk about that a little bit later, but small concentrations of boron can lead to trouble. The next pair reaction is more interesting because it's a two-step reaction. Nickel 58 is a common isotope of nickel. It's about 63% abundance. It absorbs a thermal neutron to form nickel 59. The telephone is a gamma. Nickel 59 also has a significant thermal neutron absorption cross-section, and it leads to iron 56, the common stable isotope of iron, and an alpha particle. So this can be a very significant source of nickel thermal reactor. Another source is just decay of tritium. Tritium decays by beta. It's a beta and an antineutrino. But the important point is the recoiling and coiling nucleus is helium-3. And this leads to severe problems, actually, in some of the tritium production reactors at Savannah River. And the reaction can also be exploited as a method of generating helium to study helium effects in materials. Well, helium is insoluble in metals. Talking about helium is so bad. Now, why is it bad? It's insoluble in the metals and diffuses to grain boundaries where it can cause severe embrittlement. Now, if you look at this fracture surface, remember metals are crystalline. We have fairly fine grains, and you can see from this fracture surface that this material has fractured along the grain boundaries. That's what we call an intergranular fracture. But you'll also notice that the boundaries are completely covered with bubbles. And this material is Inconel 600. It's a high-temperature nickel alloy. Used to be popular steam generator material, though there you don't have a neutron flux to worry about. It has been irradiated in the high-flux isotope reactor at Oak Ridge, producing about 1,800 ppm helium through the two-step nickel reaction at 650C. And this is probably one of the worst cases of helium embrittlement I've seen. You can continue irradiation and probably make it fall apart on the grain boundaries and produce metallic sand, if you like.
What amplification is that?
What application?
Amplification, when you look at grain boundaries, what?
Oh, the magnification?
Yeah.
I didn't read it, but 200 is pretty common, 200, 500. Well, we said that fission reactors can be used for both accelerated testing for fission and fusion reactors. I told you a little bit about that. We're going to show you some methods in just a few minutes. This is a picture of the high-flux isotope reactor at Oak Ridge during a refueling operation. This reactor has either the highest or the second highest thermal flux in the world. The price to pay for that is that the entire core has to be renewed every 23 days. So it has a short fuel cycle, and you can see in the picture where they're removing the inner fuel element from the reactor vessel under about 20 feet of water at that point. So this is the workhorse reactor at Oak Ridge. I'm going to show a lot of data that have come from HIFER irradiations. Well, research reactors can be used to study helium effects because they have a high thermal flux. And we talked about that two-step nickel reaction, which will produce helium. And here's a case where we're going to exploit it to our benefit. We're going to intentionally produce helium in materials so we can study what will happen in cases, for example, of fusion reactions. Here we have a plot of helium generation as a function of displacements per atom. And the problem here is that research reactors can produce levels of helium in stainless steels that are far too high to simulate fusion reactor conditions. 50 atomic ppm per dPa as opposed to the desired 12. Well, here we've plotted a line with a slope of 12 showing the desired production rate for fusion. And now we want to be clever about producing the right amount in a simulation. And what's done here, this particular radiation is for the ORR, the Oak Ridge Research Reactor. We start with our materials just surrounded by water to burn in nickel 59. Then, before it gets too high a concentration, the core piece is replaced to displace the water. So we put aluminum in place of the water to harden the spectrum. And then, a little further on, it has to be replaced by hafnium to absorb the thermal neutrons to get the helium production under control. And at that point, it will track the correct helium dPa ratio. So this is one of the techniques, one way that we use the fission reactors to simulate fusion reactor behavior. There's another technique. If we have some alloys with low nickel contents, we can increase the nickel by nickel doping to produce the correct helium, the dPa level. And here we're looking at an alloy. I hope you can read it better than I can. It's a common alloy of 12 chrome 1 moly with 0.2% nickel. If we irradiate that, we get far below the desired cross-hatched region, but if we can increase the nickel to 2%, we can produce the desired amount of helium. Can also inject materials with helium from a cyclotron and then follow them with neutron irradiation. Now here's a case of vanadium alloy where we don't have any nickel. We can't use that neutron two-step reaction. So these have been cyclotron implanted. And if we look on this plot of elongation as a function of temperature, we see that the control has ductility increasing with temperature, which we'd expect, but if it has helium in it, we're down here with a very significant drop in ductility. So we're showing several techniques, and the reason is that when you're doing simulations and studying the fundamental behavior, one technique will not do it. You need every piece to the puzzle that you can get. So we use various techniques. For example, if you're going to dope with nickel, you have to understand the effect of adding the additional nickel. So one experiment cannot simulate behavior. Another problem is that neutron radiation usually, in fact most always, produces intensely radioactive materials, which then necessitates remote handling. So when we generated these data, we showed all of these tests are done behind 3 to 5 feet of high-density concrete and maybe 3 feet of lead glass, or a tank filled with, in this case it's a tank filled with zinc bromide solution. Then all the materials are handled remotely with manipulators. In this case, we have an ultra-high vacuum chamber that's operated entirely remotely. Okay, I think that's the next line. Okay, I said we'd talk about our radiation creep. Well, let me first talk about creep. If we take a wire and hang a weight on it, we'll get elastic deformation, and then it will stop deforming. If we increase the temperature, then that will start to deform again. That weight will fall. And this is a phenomenon of creep. But now, if we go back to our low temperature wire, room temperature, hang a weight on it, it sits there, now put it in a radiation field, it will deform. So for radiation creep, we need two things. We need a stress and we need a radiation field. To put it in perspective, if we tighten a bolt, in this case we're preloading it to a stress of 250 MPa, it's a pretty tight bolt, and irradiate it by the time we get to 10 dPa, 10 displacements per atom, we've completely relieved the stress in that bolt. So one thing it's telling us, if you're going to fasten materials in a high flux region, don't bolt it. Other thing it's saying is this is a phenomenon that can sometimes be useful, because if we have stresses resulting from swelling, or in some cases thermal stress, radiation creep can be beneficial and relieve these stresses. But the earliest record of a radiation creep is in uranium, and this was described at the first and second Atoms for Peace conferences in Geneva from some Russian work. And notice here we have a stress applied. When the stress is removed, the material stops deforming, or by a stress, shut down the reactor, the material stops deforming. So we need, again, the two things. We need the radiation and we need the stress field. Now, I said it was not a high temperature phenomenon, and here we have creep in stainless steel as a function of temperature, and in thermal creep we have deformation, but when we get down below, in this case 500 degrees, it becomes insignificant. And we know that we keep metals around at room temperature, they don't deform. The Eiffel Tower has been standing since 1889. It doesn't bend over and collapse. But if it's in an irradiation field, we see that even at the low temperatures, we have a significant creep rate that remains. And it has a very weak temperature dependence, maybe even none at all. That's quite an interesting phenomenon. Well, how do we study it? Well, Galileo had all the right ideas. He was a clever fellow. And we said we could just hang a weight on a wire. Well, he used a beam and then hung a weight on the beam to measure deformation. Things haven't changed too much. The principles are the same. We often use a pressurized tube. So we have a tube and we put it in a pressure bomb, pressurize it with helium to a desired level, and then shine a laser through a sapphire window and seal the tube. So this is a common way because they take a very little space. We can put them in a reactor and we can study quite a variety of stresses. So it's a very convenient way to study radiation creep. Well, now let's talk about some other defects. We talked about point defects in metals, talked about interstitials and vacancies. There's another kind of defect. We can take a plane of atoms, it's called a partial plane, and sandwich it into a crystal. And if we do that, notice it's a partial plane, it doesn't come all the way down. If we do that, we'll have a linear defect along the line where that plane ends. And this is called dislocation. And if we want to shear that metal, if we didn't have a dislocation there, if we want to put a stress on this plane with respect to the one above it, we'd find we had to break all these bonds. But if we had a dislocation, we can break one bond at a time, and the dislocation will kind of flip over move to the edge. And metals commonly plastically deform. Now, if we were to have a vacancy go into to the edge of that row of atoms, then effectively that row of atoms would move up one lattice constant. Or if an interstitial diffused into that site, that row would move down. So we can have dislocations, we use the term climb, up and down, by diffusing interstitials and vacancies. So they can move. And if the dislocation is tied to a defect by an elastic stress, then these defects can cause it to move around these objects and enhance plastic deformation. All right. Well, we have lots of vacancies and interstitials around. Vacancies cause it to move up, and interstitials cause it to move down. So we have both. On the average, we don't go anywhere. But if we introduce a stress, then we can change things. Because if we had a tensile stress there to pull atoms apart in that region, it would be more energetically favorable to have an interstitial there. So now we can have interstitials predominate over vacancies, and now that dislocation can move. And this is one of the mechanisms of a radiation creep. And the point is, if it can move around obstacles. Get around obstacles, then we can have glide again. So the irradiation hardening that we said resulted from putting a lot of defects in and tying up these dislocations. We only said half of that earlier, but that's what happens. Now we can get them to move around. Well, I didn't say much about temperature in this case. Here we have some irradiation creep results from, in this case, from the high flux isotope reactor. And here we see strain as a function of stress, plots for 300 and 400 degrees, and now we see another plot for 60 degrees where it's even higher. So we kind of mislead people even when we call it creep, because it's not a high temperature phenomenon, it's an irradiation phenomenon. And what's happening here at these low temperatures, interstitials are free to diffuse throughout the lattice and can be attracted to the dislocations. But the vacancies are frozen out. Temperature is too low for them to diffuse. So instead of having them balance, we have a preponderance of the interstitials, and that's causing a higher creep rate at the lower temperature. And we can even get a radiation creep at liquid nitrogen temperature. Okay, I'm going to talk about vanadium a little bit. And the first question is, why vanadium? Why would anybody want to use it in either a fission or a fusion reactor? And what I've plotted here is induced radioactivity in a fusion reactor as a function of decay time. And we have various materials here like graphite and silicon carbide, not a real exciting structural material yet. If we look at stainless steel, we notice that that curve doesn't drop very fast. And we're out here 100 years after shutdown, and we still have something that's quite radioactive. Hands-on level for recycling these is probably around 10 to the minus 6. But notice vanadium, I can find it. Here we have a vanadium alloy, vanadium 20% titanium. And if we go out here to 10 years and beyond, we're orders of magnitude below stainless steel. So, if you have a structure like a fusion reactor made from vanadium, then at the end of its useful life, you have a chance of recycling it, or at least if you have to, burying it. Recycling is favored. The structural materials in a fusion reactor will activate to the point where maintenance on the machine has to be done remotely. And the disposal and recycling, of course, will be difficult. So vanadium is looked at as a low activation material. Especially true in Europe, where they're more sensitive to disposal of radioactive materials. So we're looking at vanadium as a fusion reactor material. And the vanadium system would be cooled by lithium. Two reasons. One is that lithium can be used to generate tritium to fuel the reactor. The other is that lithium is compatible with vanadium as a coolant. Water or gas would not be, because you can't, for example, get helium pure enough to not embrittle the vanadium. Lithium, in the case of lithium, primary contaminant is oxygen, and the oxygen will primarily go into the lithium rather than the vanadium. So it's a nice material for vanadium. But if you're going to use lithium, special handling is required, particularly a very high purity argon atmosphere. So the work with lithium is done in a high purity argon glove box. And in this glove box, we keep oxygen, moisture, and nitrogen below 1 ppm. Well, from the study, we said that in the case of lithium in contact with the vanadium, oxygen will preferentially accumulate in the lithium. So here we have creep strain, done with pressurized tubes again, done in the case of vanadium in lithium, and the green curve is vanadium in a vacuum. And you can see that the creep rate is much higher in the case where we don't have impurity atoms impeding the dislocation motion. So it's a softer material when we remove the oxygen, and we get a higher creep rate. And needless to say, if you're going to use this as a structural material, you better know what the creep rate is. Well, transmutation helium is also important in fission reactors. Repair welds are difficult or even impossible with helium concentrations as low as 1 to 10 atomic ppm. And here is an example. We have stainless steel with just 5 ppm helium. We've attempted to make a repair weld, and you can see it doesn't look great. And here we had it cracked. They have a fracture surface that looks very crystalline. What do we call the fracture surface? What kind of fracture? Intergranular. Broke on the grain boundaries. Now if we go to a higher magnification, in this case we're really going up, this is 2000, we usually don't need it that high, we notice something very strange about the grain facets. They're all full of bubbles. When you look at it with higher mag, indeed, they are just coated with bubbles. And the bubbles link up, the material falls apart. So if you wanted to make a repair weld, let's say at the upper shroud in a BWR, here's a case where it's at a very high flux, you probably couldn't do it. Again, just because of the boron, you have 10 ppm boron, leads to 10 atomic ppm helium, and with normal techniques you can't weld it. So this is one thing that's being investigated, how we might apply a compressive stress, for example. Works fine in a laboratory. I don't know how it would work in a reactor vessel. Meaning I don't know how to do it in a reactor vessel. Okay. Let me touch a little bit on another problem with transmutation. Let me first talk about burnable poisons. Burnable poisons are used in all modern reactors to homogenize the power distribution and reduce the extent of the control system required. And what I'm showing here is, if we look down the core region of an LWR, of a PWR here, if we load a critical mass of uranium, we can start a reactor. And as soon as we fission the first uranium atom, we no longer have a critical mass, so our reactor shuts down. So obviously you have to load enough uranium for the length of your fuel cycle. Well, now if you do this, of course you have to get back to criticality, so you have to put control rods in there. Well, if you really have a high fuel loading and then you put in all your control rods, you end up, when you having to just pull them a little small distance to get critical, you end up with almost all your power produced in the bottom of the core. Of course, designers can get clever about this, and they have banks of control rods, so you don't just have one bank, and that helps. But if you had a burnable poison, homogeneously distributed, and ideally one that burned at the same rate as the fuel, you wouldn't need a large control system, and then you pull the rods out and generate power throughout the core, and everybody's power out. So burnable poisons have a large benefit, and as a result, they're used. Boron is frequently used as a burnable poison, often inside the fuel pins. We've seen this reaction before, the boron-10 reaction, and remember it's producing helium. Well, helium gas generates an internal pressure in the fuel pins, and when the internal pressure exceeds the coolant pressure, you're going to have this cladding separate from the fuel, and then the centerline temperatures of the fuel are going to soar. So we don't allow that to happen. So using boron as a burnable poison can be limiting your fuel burnout. Well, other burnable poisons can be used, and they are used, but they do not burn completely. So you end up with residual reactivity at the end of your fuel cycle, and that's going to shorten the life of your fuel. It's like having a control rod stuck in there. You could run the fuel longer if you didn't have that burnable poison in there. The residual reactivity usually results from a lower sigma A isotopes, lower absorption cross-section isotopes that burn more slowly than the primary absorber. Now, if the cross-section were small enough, they wouldn't cause any problem. It's the intermediate ones that cause problems. For example, here are the stable gadolinium isotopes, and gadolinium-157 probably has the largest cross-section, absorption cross-section of any isotope. It's absolutely enormous. Gadolinium-55 is also huge, but 154 is around 60, and that one is a problem because it is an absorber, it is significant, and it doesn't burn up very fast. So by the end of the fuel cycle, it's still there. Gadolinium-156, I believe, has an epithermal cross-section that makes it a problem. Well, we could remedy that by isotope separation. And an example here is again gadolinium. Over here we plotted the macroscopic absorption cross-section as a function of time. And if we look at the total, we notice after about 3 or 4 years, we end up with the residuals in a steady state around 0.15 or so. And in this case, we have removed the gadolinium 154 and 156. And in that case, you can see that the residual is lower by roughly a factor of 5. Now this is kind of a simple calculation, not very sophisticated. And at this point we had to do a sophisticated calculation. So what happens when a metallurgist needs a sophisticated neutronics calculation is you go to somebody who's an expert in the field and you let him do it. You team up. And this is the way we do research. It would take too long for everybody to try to learn each field he has to get into. But by cooperating, we can put a lot of power to bear on a problem. So the calculations here were done by Jean-Paul Renier at Oak Ridge. And what we've done here is incorporated burnable poisons into the fuel rods. This is not unusual. They're called IFBA, Integrated Fuel Burnable Absorber Rods. We've looked at assemblies containing 8, 16, 64, and even 104 rods. And this is a case where we have a PWR fuel assembly with 64 burnable poison rods. Within a fuel rod, 4 configurations of the burnable poison were considered. One is simply to blend the burnable poison with the fuel. The other is to put the burnable poison only in the outer third of the fuel pellet. And this can be done. It can make compound fuel pellets. Another is to have a thin coating on the perimeter of the fuel pellet. It's done. Westinghouse fuel. It's the burnable poison on the fuel. It's a coating. Another idea, which I think is fairly new, is to alloy the burnable poison element with the cladding. So in this case, we'll use the burnable poison in a metallic form and alloy it. Well, Monte Carlo calculations were then made using state-of-the-art computer codes and a sequence of codes. The main one is the Monte Carlo code, the MCNP4C, and then the origin 25 to track the isotopes. And let's see, we can go into some of the details. Let me save a little bit of time. Whoops, I'm having trouble. Okay. We'll skip the details on that and go to some of the results. And what I'm plotting here is the reactivity due to burnable poison as a function of a penalty. The number of days that a reactor could be run if the residual burnable poison were not present, we'll call the residual absorber penalty, the RAP. And this can be used as a parameter to determine the benefit of our isotope separation. And what this is, if you work out your model with the burnable poison and determine how many days it will last before K effective drops below 1, then you take the burnable poison out and run the same thing and see how many days it takes to drop below drop subcritical. And the difference in that is the penalty that you paid by having that burnable poison in there. Okay, well, something very interesting is that if we plot that for each of the 4 configurations, they all lie in the same curve. So the RAP is essentially independent of the configuration. Well, that was a surprise, at least to me. I still don't understand it. But this is convenient because now the configuration is an independent parameter that we can use to adjust the burn rate. If we change the number of rods that we put the burnable poison into, now the curves are different. They don't lie in the same. And if you track some of the numbers here, and this set of curves for 16 rods versus 64, you find it doesn't hold. The curves are very different. To compare the separated isotopes with the natural element, we'll look at the following ratio. We'll look at the reactivity at end of life over reactivity, negative reactivity from the burnable poison at the beginning of life for the isotope, and compare that with the same ratio for the natural element. So if separating isotopes in the burnable poison doesn't do us any good at all, that ratio is going to be 1. The smaller it is, the better. And if we look at some of these isotopes, gadolinium-157, samarium-149, notice in this region they're all below 0.5, and depending upon the configuration, we can get them well below 0.2. So it looks like we can do a lot of good by separating isotopes, and we find the best candidates are gadolinium-157, erbium-167, samarium-149, and dysprosium and hafnium isotopes in that order. The self-shielding effect becomes apparent if we look at a simpler ratio. If we look at just the negative reactivity due to the burnable poison at end of life over beginning of life, in other words, how well does it burn up, we notice gadolinium does quite well. But let's pick any one of them, and we notice kind of what we expect. If it's homogeneous, it doesn't completely burn up, but if we spread it into a thinner coating and we have less self-shielding, it does. And if we put the burnable poison out in a clad, we go out into a region where the thermal flux is higher, so we don't have the thermal flux depression of the fuel, it will burn up even more. So this gives us, just the configuration will give us another parameter to adjust the burnable poison. Okay. Well, let me just save a little time here. Suppose we have a burnable poison that burns up completely. This is great. But if it all burns up in the first month, then it doesn't do us any good. We might as well not have it. So we better take a look at that also. If we look at the time dependence, here we have the case. We have the case of putting the burnable poison in the outer third of the fuel pellet. And if we look at these two curves, first two graphs, the first one is for the natural elements, second one is for separated isotopes. The first thing we notice is that for the case of the separated isotopes, we in general burn them more completely. Well, we already knew that. If we look at the case of gadolinium on either natural or isotope, it looks like we're burning it far too fast because after just 1 year, essentially all our burnable poison's gone. Same thing with samarium-149. But if we go to erbium-167, we find a much more uniform burnup. And the same is true for the erbium isotope as well. The others. So if we are going to have a very long fuel cycle, well, maybe we want to have a Generation 4 reactor where we don't take the head off the vessel for 4 years. We would probably have a blend of burnable poisons. We'd use those, one of the longer ones for the longer term behavior. For some of the absorbers, the isotopic separation could lead to quite a large savings. For example, here we have erbium in 16 rods. And just take a look at some of these numbers. To reach a given reactivity, let's take 0.06, we have 25 days. Penalty in the case of natural elements, in the case of separated isotopes, we're down around 5 days. We saved around 20 days. Okay? Well, in 4 years, the isotope separation benefit ranges from 6 to as high as 110 days. Now, if we look at the case of gadolinium in 16 rods, that's the one where we save 6 days. In the case of samarium-149, well, you might say, well, sure, but if a samarium is going to give you a penalty of 50 days, maybe you're not even going to use it. So we have to be careful how we use it and what we use it for. But if we just consider gadolinium, 1 day savings at the end of the fuel cycle is worth $1 million. So if you can run it just one more day, you've saved $1 million. Now, I recently presented this to the Korean Atomic Energy Research Institute, and Their feeling in Korea is that the designers, the utilities, can be clever enough with their fuel management that they think they can save that 6 days. So they're not excited about separation of isotopes for commercial reactors, but they feel it's essential for the Generation 4 reactors. Well, we talked about separating isotopes, but everybody knows that's almost a brute force technique and it's very costly. But there is a technique called plasma separation that has been used over the last 20 years, been experimented with. And here you sputter off some target material, you put it you get a plasma, you put it in a chamber with a strong magnetic field, and you drive it with microwave energy, and the radius of rotation, of revolution around the magnetic field lines is a function of the mass. The higher the mass, the larger the radius. So you can have targets at a given radius to trap a particular isotope. And here are some calculations for this process. And here, for example, for gadolinium-157, it has about a 16% natural abundance, but just one pass can take it up to 46. But what's really important is that they're talking tens of kilograms per year. Calutrons normally talk about milligrams, and here we're talking about kilograms. So finally we have a separation technique that at least has the right scale. So we can supply enough for industrial application. We are at the point now of getting ready to test this in a plasma separation device. We're now fabricating a gadolinium target and getting it ready for separation. Oops. Okay, let's skip that. So to summarize, radiation effects include swelling, embrittlement, and irradiation creep. Understanding is well enough that we can reduce their effects. What's important is that we do understand them, predict them, and learn how to live with them. The neutron spectrum is important in determining the effects of all of these, especially those associated with transmutations. We said in fusion reactors we have helium, transmutation helium, which hurts us a good deal, and we've learned how to simulate this using the opposite end of the spectrum, using the thermal spectrum in a research reactor. Radiation creep can be detrimental as well as beneficial. Again, we have to understand it and predict it. Fission research reactors can be used for accelerated radiation effects for investigation for both fission and fusion reactors. Transmutation-generated helium can lead to very serious failures in repair wells and LWRs. And this is a real problem that's receiving a lot of attention these days. Isotope separation in vulnerable poisons can reduce and extend the fuel cycle for advanced reactors. Let me leave you with a thought. There's a quote from Dr. Norman Hilberry, former director of Argonne National Laboratory, who said, "We physicists can dream up and work out all the details of power reactors based on dozens of combinations of the essentials, but it is only a paper reactor until the metallurgist tells us whether it can be built and from what." Norman Hilberry is also the original Scram. When Fermi built the first reactor, I call it the first reactor, under Stagg Field, the Squander of the Squash Courts, he had a set of safety control rods that were lifted, that were removed, and then tied with a rope. And Norman Hilberry held the axe, but if Fermi gave the signal, he could cut the rope and shut down the reactor. So I had the pleasure of talking with Dr. Hilberry several years ago, and I'm really kicking myself for not asking him whatever became of the axe that was used. I suspect it ended up in a salvage pile somewhere, but I don't know. Okay, well, thank you. Okay.
Okay, we have time for one or two questions. Any questions? Any comments? Joe?
I have sort of off the wall question. You were talking about the axe. The guy, there was an acronym for what the guy was called to cut the axe. And I can't remember it now. Do you remember what they called the guy who did that?
Oh, that was it, the SCRAM, Safety Control Rod Axeman.
I had something else.
Safety control.
I thought it was like a funny acronym. I thought there was like another part to it, like a funny part.
A funny part.
I guess I'm wrong.
I don't know.
That's funny to some people. Any other questions or comments? Okay, we do have a few new faces in the audience, but before we adjourn, I failed when I recognized the students at the beginning of today's colloquium. Before I introduced Martin, I recognized the students, but I forgot to mention the name of the professor who supervised those students, and it's Dr. Ron Peavy, and he certainly deserves some recognition too. And so I apologize for not mentioning your name. He deserves some credit. None of the money, but at least deserves some of the credit. Okay, now for the new faces in the audience, we do have refreshments downstairs, and everyone is invited, and you can then ask more questions and talk to Martin one-on-one. But before we adjourn, let's again express our appreciation to Martin for his presentation. Very good. Thank you.
Good, you?
I like it.
Are you going to be in class physically tonight?